John, do you want to get you any water?
No.
You're okay? Great. Okay, so officially welcome from Vermont Academy and from the Southern Vermont Astronomy Group. We're really excited about this partnership. And one of our students, four-year senior Eli Boxer, is going to be introducing Dr. Perry this evening. Come on up, Eli. It's going to be a little blinding.
So, Dr. John Perry earned his PhD in astrophysics from the University of Rochester. He recently retired as a senior lecturer in the physics department at the University of Vermont, where he's been sharing his knowledge with students since 1975. Dr. Perry is the founder and president of the former Holographics North, a hologram production studio and gallery located in Burlington. The studio produced hundreds of some of the largest and most detailed holograms for museums and other clients around the world between 1984 and 2019. Dr. Perry uses laser light to project his holograms, both large and small, to demonstrate how a flat informational storage surface can be expanded into three-dimensional reality. Tonight, he will help us to understand the holographic universe concept as it relates to black holes, string theories, gravity, and event horizons. Please join me in welcoming Dr. John Perry to Vermont Academy.
We've got folks coming in on Zoom this evening too, so I just wanted to welcome all of you, along with our live audience. And folks on Zoom, if you have questions, please type them into the chat, and Eric Schmidt will report them out to us. And now, officially go on stage.
Okay. Okay, let me say this first. For about the last 2 weeks, I've been kind of stumbling, having trouble getting messages from my brain to my voice. And stumbling over some language, so cut me some slack on that, and be patient if I'm stumbling as I am right now over some of this language. We can have some fun with this, basically. It was I think about 2 weeks ago, maybe 3 weeks ago, I was online and I caught a comment that somebody made that this theory, the holographic universe theory, is garbage. Complete garbage. And the only reason it exists is so that people can get up and talk about it. So here I am up talking about it. The main thing to bear in mind with this theory, the underpinnings of the whole thing, is that all the information required to define a volume of three-dimensional space, everything in that three-dimensional space, every detail of it, all that information can be recorded on a two-dimensional surface. Sound familiar? Hopefully it does, especially if you were here 20 minutes ago, because that's what a hologram does. 3D volume of space, imaged for you or projected for you to experience, all stashed really on a two-dimensional surface. So let me back up a little. That was a great intro from Eli. Let me run through it again, maybe just a little bit, getting used to this controller here. I taught astronomy, as he said, for 50 years as a lecturer, not doing research, but teaching a whole lot of courses at UVM. And during 5 of those years, I also taught a course in optical holography, a 2-semester course in optical holography. It was a lot of fun. We set up a lab over at the Living and Learning Center, if you know where that is, a laser lab. And made hundreds, maybe even thousands of holograms, which is where that came from. And during the end of that period, in 1984, I decided to start my own company downtown in Burlington in the basement of an old, big red brick school building, 6,000 square foot basement, to make large format holograms. This one is a meter by a meter. I think it's the 3rd contract we had back in 1984. The image is about 8 feet deep. It comes right through the film plane into the foreground. A company called PRC's True Color Images. You can see it's not animated though. It's just to show you a little preview of some other holograms you're going to see soon. And I'll tell you, I look at this slide and weep, but that's the way life is, I guess. First, let me tell you what is not a hologram. None of these things are holograms. Tupac dancing on stage 10 years after he died, not a hologram. Nothing to do with holography. I should have known in advance if I'm asleep here. Leah projected into the middle of the table, not a hologram, just as two-dimensional as the movie screen that you saw it on. So there are a lot of things. I could go on for half an hour about stuff. It's called holography. It is not really holography at all. Don't, by the way, be confused about this one. A holograph? Anybody know what a holograph is?
Written by one person. Written by one person.
Yes, well, a handwritten document, like a holographic will. Maybe you very unwisely scrawled just before you died. Well, really bad idea. So what is a hologram? Light wave interference pattern, all the information to describe a three-dimensional space stored as a light wave interference pattern, a very fine scale pattern in the optical case at least, on a strictly two-dimensional surface. So a two-dimensional surface, as I said a minute ago, containing all the information to describe a three-dimensional volume. It's the most efficient way we know today to store information into a small area on a 2D surface. Basically, it is, as I said before, to some of you, it is the equivalent of radio technology, but at a much, much, much shorter wavelength. You take the source of waves, in this case light waves, optical light waves from a laser. You need the organization and purity of laser light, coherent light. Split that into two beams. Something like a partially silvered mirror will do that. Some of the light will go through, some of it will reflect off. Take one of those beams, spread it out with a lens, and light up the subject with it. Pretty simple subject in this case, not what's going on, just a cube. But light up the subject with it, and a lot of that light will reflect onto the film plane. The other beam, spread it out with a lens and shine it directly at the film. So there's no information in that beam. It's just what we call the reference beam, the carrier wave in radio. You got to put it diagonal enough that the subject doesn't block that beam. Basically, it doesn't cast a shadow on the film. That's why it's coming in from an angle. You record, well, what happens in the film plane is, of course, the two beams come back together again. They meet up in the film plane. And where they meet up in phase, peak on peak, trough on trough, these waves, they add up to brighter light. Where they meet out of phase, trough on peak, peak on trough, they cancel out. So you get this barely, really sub-microscopic, almost sub-microscopic pattern of light and dark recorded on the film plane. So you record that in the emulsion. It could be a glass plate, like the one I was showing most of you, or it could be an emulsion coated onto flexible film. Either one will work fine. We work mostly on film, actually, in the company. You record it, process it, pretty similar to photographic processing, and bring it back. And bring back that diagonal beam, that so-called reference beam, shine it through the interference pattern recorded on the emulsion in the hologram. And that interference pattern now acts as a diffraction pattern. It diffracts the light, redirects it toward the viewer over here in such a complex way that it actually focuses that light to a multitude of image points out here, essentially an infinite number of different image points out here. There's nothing there. There's nothing there but light passing through. You can put your hand right there, as I did, and you'll see the image projected onto your hand, but you're not going to break your eyes or anything like that. You put your eyes over here, look back into the light, brain lights up and says, oh, I see a cube. Well, so what? You know, but, not a very interesting one. So let's see one. And this is where what I was doing a minute ago, it turns out that almost everybody here I think saw it actually. I prepared some slides and videos of what I went through starting around 6:30. Slides and videos to demonstrate that in the slides themselves. I'm glad we didn't try to do it in for an audience of this size. It wouldn't have worked to do it live during the talk. In each of these next 8 or 10 slides, you're going to see a kind of an aerial view of the table on which that whole system was set up. The laser, the hologram, let's see this one right here. The laser, the hologram, where the image is located. And on this first slide, you're going to see it behind the hologram, where the camera was over here. That little setup diagram is going to change from slide to slide to slide to show you different things, pretty much what I went through in the flesh over there a little bit ago. So here's the way that holography was originally supposed to work. You light it from behind, like that. The image would be formed behind the hologram, as it originally was with that hologram over there. And view it from here, or put the camera out here, and I see that the animation is running automatically. That's okay. The question was, is that image that you get back here really 3D? And what that little arc is telling you is that the camera is being swung around the hologram about 90 degrees or so, and you saw the animation taking place as it was. I wonder if we can run that again. I can't. Yeah, maybe if I go. Oh, thank you. So there's panning the camera to the left, or really swinging it to the left, swinging it to the right, and you can see the perspective changing, proving to you really that it is 3D. What's really happening, as I said before, the light's coming from the laser directly to the hologram, and then diffracting out toward the viewer or the camera, as if those rays had come, those light rays had come from various image points back here behind the hologram. Looking into that light, it looks like these rays came from back here. They didn't. They came from the hologram plane itself. And that's why that's a virtual image. There's no laser light actually at that volume right here where the image is. And as I was saying before, let's see, back to here again. The equations predicting holography basically indicate that we should be able to light the hologram from down here, reverse the light, basically. It's called conjugate, loosely called conjugate illumination. We should be able to put the laser down here, light it backwards this way, take the camera, now the light's moving to the left now. So got to take the camera and put it way over here because the light's going to go that way. And it should still work. It should still form an image right there in space. But now that image is in front of the hologram. The light is actually being diffracted by the hologram to those image points and then passing on through. And the camera will pick them up over here, theoretically. The equations tell us, they're not always right, of course. So as I said, it's much easier. Rather than move the laser down here, move the camera over here, let's just flip the hologram 180 degrees, and then we're illuminating it backwards. And in the act of flipping it, the image is going to go with it. So the image being back here now, we're going to illuminate it the same way, we're going to photograph it the same way, but the image is going to come rotating from here, from the back to the front. Does that work? Wait. We're not going anywhere here. Going backwards. Yeah, there's the flipped image. I don't know if I'm running this or it's me. This wasn't doing anything for me. There it is. There's the flipped image. This little blue stuff up here. Oops, daisy. The laser pointer. There. This little one more back. This little blue arc up here. I never used laser pointers in my classes. I always use the computer pointer from the remote, but I have one here. So the hologram is flipped around, and the image is out front. The image is out front. There it is. There's the whole image. And as I think I showed you before, it is, man, this thing's got a mind of its own. There it is, rotating. And if you look carefully, right now the camera is swinging to the right, and you can see that the foreground spikes are going the wrong way, basically. I'll let you figure that out for yourself. I'm getting confused myself because the slides are kind of bouncing around. So this is that really odd pseudoscopic perspective that we were talking about earlier. The background is now focused closer to you, and what was recorded is the foreground is now focused further away from you. If you think about it, that makes perfect sense. This is the hologram, and there's the image of, let's say, the foreground of the image as it was recorded are my fingertips. Now what we're going to do is flip the hologram around. It goes like that, and now what was the foreground of the image is now closer to the hologram as it was when it was made. That makes it further from you, the viewer. So you could have actually predicted that just fine. So I think you saw that rotation taking place and that weird pseudoscopic image. Now, maybe, wrong one. Oh yes, we can put a diffuser in there. I did this a little while ago. Also, you can put a diffuser right in the middle of the image itself, move it forward and back, and you'll see the image go in and out of focus as it goes. Can I trigger it from here? Oh, there we go. Oops, sorry about that. Jeez. You had it, and I lost it. There. Now we're going toward the hologram. The camera's moving, the diffuser moving closer to the hologram and then further from the hologram. And you can see that closer to the hologram, the short spikes are in focus. And further from the hologram, the tall spikes come into focus. Seems impossible to see the short spikes behind the tall spikes, but that's exactly what you're seeing in this so-called pseudoscopic perspective. There are other ways to see that. Not nearly as good as this one, though. You can take a long thin box and cut a hole for your right eye to look right through that scene. Put in 2 mirrors to put your left eye view over to the right-hand side of your right eye, and you will reverse your perspective. That's another way to get pseudoscopic, if you can follow that. Now, this is what I'm trying to get through a minute ago. You've probably heard this, that you can break the hologram or cut up a piece of film with a hologram on it, illuminate one little piece of it, and get the whole image. And I showed you that a minute ago, so I don't need to ask you if you believe it or not. Most of you have already seen it. Here's the hologram. Are we going to do it? Yeah, not going to do that with my primitive, very valuable hologram there. what we can do is take the lens off the laser, illuminate the hologram with just one little spot of laser light. The rest of the hologram might as well not be there at all. You're not illuminating it at all. So this is the setup that we're going to use. Take the lens off the laser. I put this little block in there just to indicate we just have a really narrow beam coming down. It's just illuminating a little tiny spot in the hologram. We still have it flipped around to produce an image out of front, to project that image onto a diffuser screen, a piece of ground glass. If this works, if this is true, and I know most of you have already seen it, but there it is. The whole image projected just from that one little tiny spot, smaller than a millimeter really in diameter, a little teeny spot. And it has huge depth of field, as we saw before also, because that little tiny spot is like just using the very tiny center of the lens, closing the lens aperture down to a little tiny area, and you get huge depth of field, as photographers call it. Let's say before we're illuminating this spot right here, what if we slid it over to here and illuminated some other region of the hologram plate, in this case, of the emulsion. Right now, we're seeing that image only from this one perspective, right here. That's what you put your eye right there. That's what you would see. If you move your eye over here, or move the beam illuminating the hologram over here, you're going to see the image from that perspective, a little bit different angle of view of the image. So we can try that by scanning the beam back and forth. And this one, move on to the next slide then. Yeah, there we go. So now we're going to scan the laser beam back and forth across the hologram, and we still have a diffuser out front, so we're still projecting a two-dimensional image onto that two-dimensional diffuser plane, and let's see it rotate. Took me a minute to get back to the laser from the camera to make this happen, but there's scanning side to side, and here is scanning the beam up to down across the height of the hologram. I didn't say right at the beginning, all these areas where you see white in these images, that's just overexposure in the camera. It's as simple as that. That's why they look white. When you look at the hologram itself, it's all red. It's all the color of the laser light that you're illuminating it with. But this image, this way of illuminating a hologram, just a little spot, also has a drawback, you might say. First of all, well, there's the rotation again. Let me go back again. Whoop, sorry about that. Went too far. Way too far. The resolution, sharpness, the amount of optical information that you're getting from that little tiny spot of the hologram isn't very good. The smaller that spot becomes, the less the resolution of the image. That photograph right here, this is just a zoomed in region of the central part of the image. We're still getting the whole image. I'm just showing you part of it, so you can see it somewhat magnified. This was actually with a beam of about 1/4 of a millimeter in size, hitting the hologram, 1/4 of a millimeter in diameter, hitting the hologram. Still getting a lot of optical information out here. The resolution's getting pretty bad, but that still represents a lot of information from that little tiny spot. So enough of that really ancient, primitive, simple hologram. Other holograms that we made in Holographics North, I really got to apologize for my voice. It's pretty bad these days. I have to see my doctor right away, I think. But basically, here's one we made back in 2004 for a Japanese client. It's about, written right over there, the size of it. The image is about 8 feet deep. This hand, my hand right there, is wrapped around the dragon's lower jaw, about 2 feet in front. The tail of the dragon, you can't quite see the tip of it, but it goes all the way back to that brick wall back there, and that's about 6 feet back behind the hologram plane. I've got that finger right on the film plane, which is where your knee is, or her knee is their knee. It's a single color hologram. It's not animated. In many ways, it's still a pretty simple hologram, but it's nice and big and nice and bright, and it's being illuminated with an MR16 halogen bulb. Nothing fancy. You don't need laser light anymore to light most of the holograms that are being made. Sort of tipped my hand already with this thing a little bit, but the royal portrait of the Queen in 2004 was a hologram. And we made the hologram in Burlington. She did not come to Burlington. This was made from 200 JPEG black and white flat photographs of her appearing to rotate. They slid the camera by her at Buckingham Palace. It's about twice life size. This one with John McCardle, it is animated. That's the official portrait of the president of, the then president of Middleburg. And as you walk by this hologram, it moves. He moves. It's animated. It's about life size. And he breaks into this boyish smile and then hands you the Middlebury walking stick, which every graduate gets at commencement. We've worked with a lot of artists, about 65 artists. We made I think it was about 20 holograms for artists. Canadian artist Michael Snow for the Expo in Vancouver in '86. Really great stuff, wonderful artist. I had about a 6-year project for James Turrell, about 30 holograms we produced for American artists. James Turrell, probably the best known American artist today, alive today, I would say. That one's 6 feet. Ooh, I can't do anything by mistake. This thing goes fast. It is about 6 feet tall. It is 6 feet tall, and this was these triangles come out about 3 feet in front. They meet at the film plane, and this was at one of the shows of these holograms at one of the Pace Galleries in New York about 20 years ago. We've done a lot of scientific work. This Jet Propulsion Lab sent us this model right here, and we made a hologram of it with Saturn and Titan in the background. This is the computed dark matter distribution in our universe. A small chunk of the universe, showing where all the mass, mostly dark matter, is hanging out, basically, as computed from one of the inflationary Big Bang models, just theoretically computing how that distribution should have evolved over 14 billion years. The calculation was done at Los Alamos and their supercomputer about 20 years ago also, a little bit outdated, and we made this for them. This one up here is just a stock image. We thought it would be a good one to have, to show people and sell to people. The full color Earth in the background, it's about that big, spins slowly just behind the film plane. And the moon is about 5 feet in front of the film plane. So as you walk by the hologram to the left, that moon goes ripping by to the right, just due to the perspective change. You just see it really go flying by. And if you don't recognize it, if you didn't recognize it before, that's the backside of the moon, right? It's what you would see in that perspective. That's about, that hologram's about that big, something like that. This one for the, get used to these pointers. This one, back in. Okay, there. This one, for the Niagara. For the Niagara Museum, we made this way back about 30 years ago. It's about 6 feet deep or so. This one, it was the first hologram we ever made. It's a cutaway model of a JT, Pratt Whitney JT90 engine, the kind that you fly on a lot of commercial flights. This is a Mercedes boat engine, an 8-scale model of one. Just to show you that, of course, we can make holograms of cutaway models. No problem. Just light them up with laser light and we can make the hologram. But we can also take the insides of something and put it in where it belongs, into the outer shell of that object. This one, you can walk up to this hologram. Well, it's not that big. It's 12 by 16 inches, this big. You can walk right up to it and put your eye right up to the eyepiece right here and look through it, and it opens up. So the view opens up, and you see a magnified image of the circuit board. This one over here, I can't get used to these things. This one is your brain, or anybody's brain, basically. All the different parts of your brain are nested inside each other, right where they should be, basically, in space. Yeah. Let's put it under here. Yeah. Yeah, you need to do a sound check. You can do it on the voice now. That is, as long as it stays. Yeah, it'll stay. This is about life size, and the model we hired for this one, she came with a tuxedo. We told her to do this. Bring a tuxedo. She also bought a dancing cane with a tuxedo. And so as you walk by that hologram, she takes a little step and plants the cane, and that skeleton, computer animated skeleton, moves right along with her inside her. It's really great to see. Okay, I promised animation, and bear in mind as you watch this animation that horizon back there is about 6 feet back, and the snout of the T-Rex is about 2 feet in front of the film plane as you watch this animation. Of course, it's computer animated. We're not raising dinosaurs at Holographics North, but there it goes. Run it one more time, if you can, just to, or I could back and forward it. There we go. To get a little bit of what we call a time smear in holography, a little bit of blurring, step-by-step blurring in the nose because it's moving it so fast and it's so far in front. But I'd say half of the last 100 holograms that we made at Holographics North were animated holograms like this. A multi-step process to get to the final hologram. It's not nearly as simple as what I showed about 20 minutes ago. Here's one more animated one. The man in it worked at my company for about 5 years. He was also a painter. And we'll try to run that maybe. There it goes. It's our little joke on two-dimensional art. Okay, so what does all this have to do with the universe? You're probably asking right now. Who cares as far as the universe goes, as far as astronomy goes? And of course, the idea is that, as I've said before, all the information required to describe everything in our universe, everything within our observable universe, is actually recorded on a two-dimensional surface. That could be a flat surface. More likely, it would be a spherical surface surrounding us. That's not the important thing. Could it be, basically? Don't worry about how that information is recorded. It probably would not be a light wave interference pattern, probably some more sophisticated way to store information. Don't worry about how it's illuminated or how that projection actually takes place. Those are works in progress right now. We have no proof of this, none. We have a number of hints in modern physics, and we'll run through some of those right now. Now, we'll start with something really basic. Let's suppose you're a really boring person, or you just ran out of money, you want to build a hotel, but for one reason or another, you decide to build a hotel that has no windows and only one door, and that door is usually closed when no one's going in or out. So you can't see into your hotel. Don't ask yourself why you're doing this, you'll see in a minute. You want to know how many people are in there at any given time. How many guests do you have in the hotel? Or how many employees do you have in the hotel? Or what's being served for dinner? How many chairs are in there? Any kind of information about how you're going to find out that stuff when the hotel is opaque without going in yourself, which you don't want to do for some reason. Think about that. How are you going to know what's going on in there? The answer is really easy. Hire a doorman, give him a counter, and tell him to keep track. You know, who goes in, who goes out, what goes in, what goes out, and write it on the outside wall someplace. Then you're going to always know what's going on inside your hotel without having to go in. Probably most of you know that a hotel is not completely opaque. Nothing's completely opaque in physics. It'll be at some temperature greater than absolute zero, so it's also going to be radiating some light just because of the warmth of the outside walls. But what do we know in physics? It is opaque, at least almost totally opaque. Anybody want to say, actually, what do we know in physics? I'll treat this more like a class right now. Yeah? Something you've all heard, probably know quite a bit about. A black hole. So let's back up to the beginning of black holes. Basically, general relativity, there are two relativity theories, both from Einstein. General relativity predicts that mass curves the space and time around it. I think most of you have heard that. It dilates the time, slows it down, you might say. It compresses the space, shortens the space. And if you don't believe it, then don't use your GPS, because it depends on that time dilation being corrected all the time, continually. Otherwise, it's going to send you into the Connecticut River or something like that. So every mass, even your mass of your body, has what's called an event horizon around it. We'll talk about what that is in just a minute, but for your body, most of it in this room, for your body, it's going to be really tiny. The radius of that event horizon for your body probably going to be about a billionth the size of a hydrogen atom. Really, really tiny. The event horizon for the Earth is about a third of an inch, about the size of a marble. If you take, but every mass has an event horizon. It's in there somewhere, centered on your center of mass. You have an event horizon. It's when you take all your mass and stuff it inside that event horizon that it becomes a black hole. So imagine taking your entire body and stuffing it inside that little billionth the size of a hydrogen atom size. When you get that close, to that mass, whatever amount of mass it might be. When you get close to the event horizon, space and time becomes so curved, so steeply curved, that no line of space leads outward. Any line of space that starts leading outward reverses on itself and falls right back in again. That dimension itself, that axis of space itself. So nothing can escape. Anything that tries to escape, a massive object, light itself, even light itself, it tries. It tries to move outward. Tries to move outward, but
Yeah,
Let me just turn it off for a
is
second.
it right?
you're stuck in a black hole right now.
Let's take it again.
Oh, you mistake.
I think, we're gonna go theater style. Like this, Nick? So sorry.
Between this and my faltering speech,
Doing
having
great.
a hard time here. So the result is, from the event horizon, that distance from the center of the mass, nothing can escape. Massive objects can't escape. Light itself can't escape. It's not really due to gravity. Light does not react to gravity. It has no mass. It's due to the curvature of the space and time by that mass, the relativistic curvature. And this raises a problem, because anything that falls through that event horizon, and that's happening all the time, stuff is falling through. Anything that falls through the event horizon into the 3D space inside is it's carrying information with it. Lots and lots of information about every single elementary particle in that object. So once the object has passed through the event horizon, that information is gone. It's gone from our universe. We cannot retrieve it again. We can't get it back. It's gone. And that's impossible. We're pretty sure quantum theory doesn't allow it. Information theory doesn't allow information to simply disappear, to get lost from our universe. And just think about it. Once a fact is known, once information is known, how do you get rid of it again? You can't. It's now a thing, you know. You can write it down on a piece of paper and burn the paper. That gets rid of the paper, but it doesn't get rid of fact. It doesn't get rid of the information that you wrote on the paper. So how are we going to solve this problem? This existed for about 15 or 20 years back in the 70s and 80s. How are we going to solve that problem? Well, think back to the hotel. How did we solve that problem? We hired a doorman and gave him a counter. We're pretty sure this is the case here, that when objects fall in through the event horizon, all the information that they carry with them that's required to describe them is stuck on the event horizon. It gets encoded on the event horizon itself, gets smeared out around the event horizon, like bits of zeros and ones. In some way, that information gets recorded. And then, to our outer parts of the universe out here, we haven't lost the information. It's still theoretically available to us, accessible to us. It may be difficult to get it back, but theoretically you could get it back. Well, that's black hole physics, and that's a lot of where it stands right now. So what does that have to do with our universe? Let's introduce a new concept called the cosmic horizon. It's how far you can see at the speed of light in the age of the universe. There are slightly different ways to define it, but that's the simplest. We think it's about 14 billion light years away from us, because that's the age of the universe, 14 billion years, 13.753, I think is our latest. So wherever, sorry, I keep doing this, wherever you are in your universe, wherever you are, you have this cosmic horizon around you. And you can't know anything outside that cosmic horizon. You have no information about what's outside of it. There hasn't been time for that information to get to you yet. Likewise, areas out there, regions outside your cosmic horizon, have no knowledge about you. You can't get any messages or any information, even at the speed of light, to those areas yet. So in that one way, the cosmic horizon is acting like an event horizon of a black hole. You can't send any information out there, anything at all, at the speed of light or any other speed, through that cosmic horizon. It's as if we're living in a black hole, and the cosmic horizon is the event horizon of that black hole. And this is what we think today. Most of us think that is the case. We ask again, so what? Well, that means if black holes, when things go into black holes, all the information that's sphered around the outside, all the information that you need to describe everything that's within that event horizon, all that information is stuck to the event horizon itself, is encoded there somehow. Doesn't it make sense then that the cosmic horizon serves that same purpose for our entire universe? All the information you need to describe everything in the universe, everything in galaxies and stars and people and cold water, anything, all that information maybe is stored on that cosmic horizon or outside the cosmic horizon. Doesn't have to be right on it, really. And the first thing you might think is the cosmic horizon big enough? Is there enough surface area on that cosmic horizon to hold all that amount of information? All the information required to describe everything in our universe, our observable universe. Well, if you want to follow it, you can. Be my guest. But first you have to calculate the surface area of the cosmic horizon. We know the radius. Take 4 pi r squared, and that will be the surface area. I put it in meters right here of that cosmic horizon. That's how much two-dimensional surface area that you have to work with. Remember, the surface of a sphere is a two-dimensional thing. It's not three-dimensional. It's a two-dimensional space curving back on itself. You only need 2 numbers to specify where on that surface you are. Latitude and longitude, for instance. It's two-dimensional. Then you have to think about what's the smallest area that you can pack a bit of information into. And we think that's what's called the Planck area right down here. A Planck length is the smallest length that we think exists in the universe, in our universe. That space is actually comes in pixels, basically, pixelated space in time. There's a Planck length, a Planck time, and a Planck mass, and we think that those times and lengths are the smallest ones that can exist. So the smallest surface area, two-dimensional area that you can pack any information into would probably be that Planck length squared. Something like that, or maybe a circular area, the radius of the Planck length, approximately. So take the area of the cosmic horizon, divide it by the smallest area that you can put a bit of information into, and you get the number of bits of information that you can stash or encode somehow on that cosmic horizon. It comes out to be, whatever here, 10 to the 123rd bits of information. Approximately. You can put different assumptions there, here and there. But you gotta come out with something like that. How many bits of information are required to describe every detail of our universe? That's been estimated many times. And usually it comes out to something like 10 to the 81st bits. 10 to the 70th, 10 to the 90th, something like that. So clearly, there's plenty of area, You can pack more information than you'd have to, basically, onto that surface of the cosmic horizon in order to describe our whole universe, every detail of the universe. So that one checks out. That's a hint that we have from black hole physics, basically. Closely related to that is something called, it harks back to gravitational time dilation. As you get closer and closer and closer to an amount of mass, time will dilate as seen by somebody else. Let me give an example. You take a friend of yours, not probably for long, but take a friend of yours and say, I would send you over that black hole. I want you to go right through the event horizon, and go right into the black hole. Carry this clock with you, because I want to see time dilation if it really happens. This is why we have to correct. One of the two reasons we have to correct GPS clocks all the time, actually, just due to the Earth's mass. So your friend takes off, gets closer and closer to the black hole, and as they get closer and closer to that black hole, you see way out there far away in space, in flat space, you see the curvature of space and time taking effect, especially time dilation. You see their clock ticking slower and slower and slower. This is what you see out there as they approach the event horizon. And at the event horizon, right at the event horizon, that time dilation becomes infinite. Their clock, as you see it, has come to a standstill. Now, if you think that sounds crazy, we have observed it many times with things orbiting around black holes. So this is what happens. So you never actually see your friend over the event horizon. All their information gets smeared out over the event horizon, over the area of the event horizon, eternally, basically, forever. You never see them go through. The traveler, however, your friend, doesn't see any of that time dilation taking place. You're really living in two different relativistic realities. You're in different relativistic frames of reference, as it's put. So your friend just sees constant acceleration right through the event horizon into the 3D space inside. So after they've gone through, you see all their information smeared out over the two-dimensional event horizon forever. They see, your friend sees all their information in the 3D space inside the event horizon. It's a duality, it's an equivalence, if you like, in physics. So, two different ways of looking at the same thing with very different results, basically. That may or may not suggest to you that all their information, let me back up, all of her information is stuck on the event horizon, two-dimensional event horizon, and also existing inside in 3D at the same time. So does that mean that the two-dimensional data is projecting the 3D data inside it? Or does it mean that everything that fell through and became that 3D data inside created the data on the event horizon? Which way does it go? Chicken or egg? And really it's a meaningless question. It's both, really, it's both. We'll go to something totally different. Another hint that we get. The standard model of elementary particles has reigned for 60 years as the best way to describe the smallest particles that we think exist. The fermions over here on the left, all these guys over here, describe little massive particles, electrons and mesons and things like that, quite successfully. The mass of each one is given right up there in terms of its energy divided by c squared. That gives the mass. The fermions I got this backwards. Those are the fermions. The bosons over here are particles that produce forces. We think of, in particle physics, we think of forces as being transmitted from one object to another by particles passing between them at the speed of light. So these pretty successfully describe the forces that we know, the four basic forces that we know in our universe, except one, gravity. A particle physics version of the force of gravity, we just can't get it. We can't work it out. The so-called graviton over here, the particle that would transmit gravity from one particle from one object to another, we can't work it out in the elementary physics zoo, as they call it, of elementary particles. At about the same time, about 60 years ago, though, string theory was being basically invented, another way to think about elementary particles. It was not invented to answer that question about gravity. That wasn't the point. Originally, it wasn't the point. String theory kind of loped along, dying, starting again, dying, starting again, for about 60 years. The idea was to eliminate some infinities that you get from the basic, the standard model of particles. For instance, you take two electrons. They're considered point masses. They have no size. They have no diameter, no radius. So you can put it exactly the same place in space, right on top of each other at any given time. And then the repulsive electrostatic force between them is infinite. How do you deal with that? The gravitational potential, electrostatic potential energy between them is infinite. How do you deal with that? To get rid of those infinities, they said, well, instead of considering these elementary particles as little points, little point masses, let's give them some length in one dimension. Then you can't put them exactly in the same place at the same time, and you get rid of these infinities. You need a lot of dimensions for this to work, either 10 plus time or 20 plus time, depending on which string theory you like best. And as strings do, they can vibrate in a number of different modes of vibration, just up and down, or like this, or like that. And the different modes of vibration describe different properties of different parameters. Basically, the different modes of vibration represent different elementary particles. One of the beauties of this is you can describe quantum gravity, the smallest amount of gravity on a tiny scale can be described by string theory. So physicists are trying to fit gravity meaningfully into a string theory system, basically. And it was about 20 years ago that this duality, this equivalent way of thinking of things, of realities, was discovered. It's called the ADS-CFT duality. It's a tough one. This is a tough one to get, or to describe, I should say. ADS stands for anti-de Sitter space. That basically means negatively curved space, which we don't think our universe is, unfortunately. And CFT stands for conformal field theory, or theories. Fields, like force fields, obey certain symmetries, very well-defined symmetries. And basically what that duality tells you is that you could describe quantum gravity, a graviton basically, in 3D ADS space, arising from a field theory, a perfectly normal field theory, on a two-dimensional space. If the universe were a two-dimensional hologram projecting all of our information for us to sense and enjoy, then gravity would automatically be included in that information. It kind of pops up from the theories, the two-dimensional theories that are obeyed on that two-dimensional holographic surface. I struggled with ways, even when I could speak clearly, I struggled with ways to explain this clearly. Part of the reason, I'm not a string theorist, I'm not a particle theorist. Part of the reason is probably that I don't fully understand it myself. That really is a tough one to get. Here's another hint, though, somewhat related to that. Quantum entanglement exists, is predicted by quantum theory, and it has been verified thousands of times also in laboratory experiments, in fact. Two particles can be entangled if they're both created by the same quantum event, like a nuclear transformation. So two electrons can be entangled, two photons, light waves can be entangled. If they are entangled and one of them changes its quantum state, for instance, its angular momentum flips from rotating this way to rotating that way, which happens spontaneously. When one of them changes its quantum state, the other entangled particle also changes its quantum state instantly, immediately, simultaneously, at exactly the same time, no matter how far apart they are. Many of you have probably probably already heard about this. So you can have one entangled particle at one end of the universe, and at the other end of the universe have its entangled pair. One of them changes its quantum state, and the first one spontaneously, immediately changes its quantum state. There are certain rules that have to be obeyed, but and of course not all particles are entangled. You have to make them, basically, have to produce them in nuclear reactions. This certainly seems to break we always think of it as the universal speed limit in our universe of the speed of light, that nothing can go faster than the speed of light. Information cannot be transferred faster than the speed of light. So how does one of them know, when the other one changes? In the string theory version of somewhat loosely describing the string theory version of the holographic universe, two particles may actually represent the same particle seen from different perspectives in 11-dimensional space or 20, perhaps 21-dimensional space. Is this going to be my next slide? I'm not sure. Let's see. So those two entangled particles, no matter how far apart they appear to be to you, that distance between them might just be a matter of looking at them from different perspectives in a higher dimensionality. Think of the time axis, for instance. Physicists think of time as the fourth dimension. It has an axis. We're drifting down that axis toward the future uncontrollably. We can't seem to go back. We can't seem to accelerate forward or stop. Who knows why, but that's the time axis. Let's say you have you have a hummingbird feeder out in your yard, and you look out the window from your kitchen, and you say, oh, there's a hummingbird feeder. I got a hummingbird. Great. You come back an hour later, and you got another hummingbird out there. Great, isn't that wonderful? And then you realize, wait a minute, that's the same hummingbird. He's just come back again, that's all. It's really the same hummingbird. And the space of time, the length of time between the two observations is the difference in perspective that you're looking at. It looked to you like two hummingbirds. It's really the same one separated by some time in between them. Try to imagine that in 11-dimensional space. That these two particles, entangled particles, are really the same particle, and the distance between them is just an illusion due to the different perspectives that you're taking on them in that multi-dimensionality. If that's true, that's another indication of the holographic principle with string theory attached, basically. I think I got one more here. String theory leads to the existence of brains. These are multi-dimensional things in string theory that have 0 dimension, that would be a point. They could be 1-dimensional, that would be a string. 2 dimensions, that would be a vibrating membrane, 2-dimensional membrane as we know them. And our universe, by string theorists, is considered to be a 3-dimensional brain. A Dirichlet 3 brain, as they call it. D doesn't stand for dimension, actually. It stands for Dirichlet. Came up with some of this theory. This is a picture of a 6-dimensional object, as I understand it. X, Y, Z is implied by the perspective, so that's 3 dimensions. Color, hue, the hue of the color, blue or green or red, is a 4th dimension. It points to any one point, any image point on here on the screen, and say, what color is it? How saturated is that color? That's the 5th dimension. How bright or dark is it? That's the 6th dimension. I think that's what you get from these diagrams. So, some cosmologists and string theorists think that these three-dimensional brains are actually floating around in that 11-dimensional space. We don't have a word for that. We don't know what it's filled with, that 11-dimensional space. So we call it the bulk often. It's just the bulk, whatever that is. But we think that those brains will attract each other, and when they collide, the enormous amount of energy involved in that collision, and that would trigger a Big Bang. It would trigger one of those brains to start, we might say this, the 3-dimensional space within it expanding, which is what happened in the Big Bang. If this is true, pretty hard to test, but if this is true, that's another indication, another green check, another hint, really, that our universe may be really a string theory brain, and all the information within our universe is existing on that 2 plus 1, 2 plus time dimensional brain. I think I'm out of hints here. There's just one question really left, and maybe you could imagine what it is that harks back to what I meant right at the beginning, what I came across online, the comment that I came across. Right. You're going to live your life, whether you want it or not. You're going to experience the reality that you experience, even if you don't like it, whether you want to or not. So, really, who cares about that? What difference does it make where that reality is coming from? And the best answer I would give you is reality. The key word here is reality. The reality, as you think of it, is under serious threat by modern physics today. It really isn't what we always thought it was. Just by walking across this room, due to relativity, I'm living in a different scale of space and time than you are. But it doesn't matter which way I walk. I'm living in a different scale of space and time. To me, that's pretty fundamental to my reality. It's the space and time that I live in. Luckily, in our daily lives, we can't measure differences in time that accurately. We can do it in laboratories, and a million times. We have to correct for that difference in time when we send in space, when we send interplanetary probes like to Mars. We have to correct for it, or we're going to miss Mars due to the sun's mass. We have to correct for it. So luckily, we don't notice those little tiny differences just from walking or driving or flying in an airplane. Those relativistic corrections or changes really don't matter much. We ignore it, basically, but it's there. Those changes are there. You fly to San Francisco and back, you are a little younger to the person who stayed home. It's so slight that who cares? I can hold my finger up and say, okay, this is exactly where my index finger, right here. Quantum theory says, no, that's not true. All the particles that make up that finger are always in a slightly uncertain position. They're kind of dancing around from place to place to place. You can't say exactly where they are. And luckily, in our daily lives, we can't measure positions that accurately either. We can do it in lab experiments, but driving down here, driving home, walking around the stage, I don't care about that teeny differences between quantum reality and the emergent reality of the real experience. What I'm getting at is, as the years roll by right now, and we're moving faster and faster through space, with spaceships, basically, and we're examining things on a finer and finer and finer scale, we're eventually going to run into a barrier where we have to redesign our concept of reality. We think of reality as being a unique thing. I don't think that way at all as a physicist. There is no unique reality. Forget it, you know. So I would say the more we can learn about the nature of reality, the better we're going to be in the next 100 years, where we start really flying around fast and looking at little teeny things. That's my last slide, and that's my last statement. And again, my apologies for my faltering speech. I've got to see my doctor very soon to see what this thing is. That's it. If you have any questions, there weren't any during the talk, you're welcome to ask them now, if you have any. I may or may not be able to answer them for you.
Did you have questions from the Zoom room?
Yes.
Okay.
If you don't mind repeating the question so that the Zoom people can hear.
Sure.
So we had a question, can you create holograms, which are apparently generated by AI algorithms to take video from a single viewpoint like a smartphone camera and perform volumetric reconstruction to create 3D models or holograms to be viewed in a VR or light display?
Yes. Yes, you can make a hologram just from one perspective using volumetric software, basically, to use shadows, to mostly shading and shadows, to turn that 2D image into a 3D image of the image or volume of space. But most of that work is done in the computer. Most of that work is just converting all that data into a 3D image, basically. To make a hologram of a 3D image when you don't have the subject, or if the subject is unsuitable for making a hologram, maybe it moves too fast, stuff like that, you can work from a series of two-dimensional photographs, each photograph seeing the model from a slightly different angle. In our system, a third of a degree. 200 JPEG photographs, black and white JPEG photographs, in fact, looking at a subject, if it were rotating, a third of a degree per photographic frame. And then from all of those different perspectives on the subject, we can build up the hologram kind of vertical slice by vertical slice by vertical slice. When you look through two of those slices on the hologram, your left eye is looking through one of those perspectives, your right eye is looking through another one, about 10 slices away, representing the parallax between your eyes. This is called a stereogram, holographic stereogram. Then you can also animate the image from frame to frame to frame. holograms you saw earlier in the slides were made as holographic stereograms, as they are. The hologram making process is the same, but the preparation of the image can be from a series of photographs, from a computer animation, or it could be from a volumetric data set from a two-dimensional image, if that answers the question. Yeah.
Can you define information?
Yeah. A lot of physicists now are thinking that that really is the basis of our whole universe. Oh, I'm sorry. Can I define information? Can anyone define information? That's the question. As I was saying, a lot of physicists think that information is the only true basic fact in our universe. It's all made of information. That's really all there is information. And it manifests itself in physical objects, certain distances apart, in space and time itself. So information is a known fact, I guess. Any known fact, I would call that information. Now, I'm also not an information theorist. Information theory, it existed when I was in college, but barely. That best answer I could probably give you. Yeah, it works. Yeah.
Related to that,
Yeah.
talk about information being, on the sphere. Does that include only physical information, or can it include like thoughts and non-physical?
Yeah. Well, your thoughts, just get into a different topic a little bit, but your thoughts are really the results of chemical reactions taking place in your brain. And all of those are described by the information on that two-dimensional surface in this theory. So if you buy the fact that all of your thoughts are really just chemical reactions, synaptic gap closings, in your brain, then that works. If you think there's more to thoughts and emotions in particular, I came across online too, is love a result of string theory? Something like that. Our emotions also, just the result of chemical reactions in your brain. As a scientist, I'd have to say yes, but I'm not sure I really buy it myself, frankly. These are unknowns. Good question. Yeah.
Is information theory part of physics? I mean, is it a branch of, what is information?
It's more, it had more to do with computers, frankly, than in any other science like physics. It started with Shannon, what was his name, back in the 1940s. This name should be right at the top of my head, and it's not. Anyway, started really thinking about how to manage information, how to move it around, how to manage it, how to specify it, how to quantify it or describe it. And a lot of computer advances in computer technology came from that work. Shannon. Yeah. That's
So, under that, like the amount of information theory that could exist and how much does information increase?
Yes, always. In information theory, actually, the amount of information in something is called entropy. They call it entropy. And it's exactly equivalent to thermodynamic entropy. It can never decrease. It can never get less. It can never disappear. At best, there's no new information. You really expect that the amount of information entropy is always increasing as the universe ages. Yeah, and that was a tough connection for me to get in the past. Was why are they calling it entropy? I think of entropy as heat and energy related to the amount of heat and energy, chaotic energy and organized energy in something. But really mean the same thing. It takes more information to describe a warm subject than a cold subject, because in a cold subject, things are locked together a little bit more chemically. So it takes more information to describe a warm subject, like ice or water, for instance. And when you look at it that way, you see it, they are exactly equivalent. One leads to the other, and the other leads to the first. Not putting that too clear.
No, I'm just sitting here thinking, so there's this amount now, and there's a limit at the cosmic, what happens?
Well, there is only so much information you could pack
Right, yeah.
onto the cosmic horizon. That's true.
Fall
What happens when you fill it up? But remember that cosmic horizon is getting bigger. Every year it gets a light year bigger. The radius of it gets a light year bigger. So there's plenty of room there. And it always will be, I think. Yeah. And it doesn't have to be on the cosmic horizon anyway. Could be stuck somewhere else. All that information. Yeah.
How do they interact with each other? Like the hologram you showed us, we can't like touch it or see it. How would we interact with each other like this chair and I can touch and feel?
Yeah.
How
I don't think anybody has an answer for that, actually. Well, the forces, all the forces that exist in our universe would also be projected from that. Just like in particle physics, forces are treated as little particles. So that two-dimensional, so-called holographic surface would also be projecting all the forces that we know. So how do you know that you're touching somebody? You feel the pressure. You feel the pressure because of the forces exerted inside your finger. So those would all be projected. Not a very good word for this really, but made real for us also by the data on that surface. It's a good question too. Yeah.
So I've got one from the Zoom audience. I'm going to
Okay.
give you the mic so they can hear.
Okay.
So,
Oh, yeah, that mic's still going there.
so is it possible that what we perceive as gravity is a manifestation of information flow or entanglement rather than a fundamental force?
Oh boy. Read it one more time just so that I can.
Is it possible that what we perceive as gravity is a manifestation of information flow or entanglement rather than a fundamental force? There's one other question I'm saving for the end for you. It's easy.
Yeah, okay. Entanglement, trying to see a connection there, I would say no, but a competing theory to the holographic universe theory is called loop quantum gravity. Quantum loop, which way does it go? Loop gravity, where gravity doesn't exist, and instead space is imagined as little loops in space, little circulating loops in space, which are constantly moving around. So the curvature of space, which produces the illusion of gravity in general relativity, it's really a curvature of space, not really a force of gravity, is created by those little moving loops of space and time, as I understand it. I don't know much about loop gravity, frankly, the loop gravity theory. Maybe that answers part of that question. I'm not really sure. Made me think of one other thing, though, that I've already forgotten, so maybe it'll come back to me. Maybe it will, maybe it won't. Think about that for a second. Go on. Was there another one? Is it or?
There was. Anybody else in the audience want? Okay. So the next question from the Zoom audience is, what does it mean for a fact to be, quote, known?
Right. That's like, what does it mean in physics to observe something? Who's the observer, and how do you know that the observation has really taken place? In quantum physics, there's a thing called quantum superposition, where every quantum particle is in every possible state that it could be in, every possible quantum state that it could be in, all at the same time. It could be here and here and here and here and here, moving that fast and this fast and this fast, all at the same time, until it's observed. And it's when it's observed, let's just put it that, when it's observed, that superposition, as it's called, of quantum states, collapses to just one of those values for each parameter. And from then on, it keeps that value. It obeys that value. It's called quantum superposition. In that case, a little bit different. In that case, what is an observation? Who's the observer? If my used to keep goats, milking goats. If my goat sees something, is that an observation? Does that collapse those quantum superpositions? Presumably. I've learned to talk to the goat to figure out what she saw. We don't know. We don't know what defines a quantum observation or a quantum observer. Likewise, I think that a fact, a known fact, I'm not sure there is a definition of what makes a fact known, what makes knowledge, basically. I don't know, if your Zoom person asks a information theorist, they'll probably have a better answer, but I don't know really. Good question too, yeah.
Well, based on that, we say observing something changes it. So if we're observing the universe holographically or however, is that changing the universe by our observing it?
Right. A lot of cosmologists think that we are creating the past by examining it. That the past didn't exist until we looked at it, until we observed it. So what happened at the Big Bang? Were there any observers, whatever that means, when the Big Bang happened? Presumably not. So how was there any reality at all? But yeah, another very good question. Are we really creating our own history by asking questions about it? I think that all bears on this subject of many physicists stating the fundamental property of our universe is just information. That's producing everything else.
Once and twice. All right, we have one more question from Zoom.
Okay, I'll do what I can for you.
So keeping in mind that you need to go home at some point tonight, as we do, I believe this question is serious. Please explain entropy and the holographic principle in dimensionality. I repeat verbatim.
Yeah. How many days do I have to answer? Entropy is really a measure of how disordered a object is, or a volume of space. Everything in a volume of space is. And so the order of things is always breaking down as the universe ages. Ice is melting, marbles are falling out of jars and ending up all over the table. That's all over the table is high entropy. Stuck in a particular pattern in a jar is low entropy. You can't presumably stuff those marbles all back in the jar, into the jar exactly as they were originally. So entropy has to keep going up. It can't go down in a closed system. I'm really having trouble putting my thoughts together. It's so hard for me right now to make the words. I'm sorry about that. What were the other, entropy and there were two other things to explain in 10 words.
Dimensionality, and I think you
Right.
I think you addressed the third sufficiently. They were asking about holographic principle and
Dimensionality is pretty easy. If you move in one dimension, you're not changing your positions in any other dimensions. That defines a dimension. I can go left or right, and I'm changing my position along that axis. I'm not changing my position vertically or front to back. So there may be, we think of dimensions as three basic space dimensions: left, right, forward, back, up, down. Time has been pretty well identified in relativity theory as a fourth dimension, just like space and just like X, Y, and Z. The difference is we don't perceive it the same way. We're stuck drifting down the time axis in the direction that we call the future. And the past, we're not in the past, we're not in the future yet, we're just at the point that we call the present, and that's moving all the time down in the direction of the future. Why do we not see time the way we see space? We don't know. Maybe we did once upon a time, and life was so boring that we gave it up. You know, why live your life if you're born and die simultaneously, and everything in between happens simultaneously? If you know everything about your life the minute you're born, give it up. That's somewhat tongue-in-cheek, which I'm having trouble doing. So that's what a dimension is, pretty simply. A line along which, doesn't have to be a straight line, but a line along which you can move and not change your position in any other dimension. Maybe three dimension, the universe may be 3, 4, 5, 6, string theory says 11 dimension. We don't know for sure. We have no direct evidence for any dimensions beyond 4, beyond space and time. We'd love to, but we don't.
Can we all give a final thank you to Dr. Perry? I so appreciate anyone who can bend my mind and just make me think about my day-to-day existence completely differently. I also want to give a huge thank you to Rick and Eric and everyone who was involved in the Southern Vermont Astronomy Group for coming out tonight and for making these presentations possible. Also to the Vermont Academy students, and can we all put a huge hands together for Nick Dunbar for running everything in the back. In the interest of not getting Dr. Perry back to Burlington too late, if there are a couple of questions as everyone is heading out, I would welcome you to maybe chat briefly. And also, thank you so much for bringing your live holograms to share with us related to this evening. So thanks all. I hope you have a lovely evening. If you have ideas for other guest speakers, please let me know. Please let Eric know.